So everyone's wrong all day long. I have the weirdest talk. It's the most different from everybody else. I don't even think I have, well, first that. Second, I don't think I have a picture of a grid in my entire talk. So that's how different I am. So I am Kevin Gott from NERSC. I'm the previous NESAP postdoc for AMReX. I'm essentially the guy running around trying to figure out cool and creative ways to fix everything. Oh, wait, that's okay. I will wing it. So what I'm currently looking into, the next object on my list of things to do, is load balancing. It feels like there's a lot of low-hanging pieces of fruit in here, things that are applicable to a wide range of AMRexers. And I'm kind of here to open up a discussion with the community that I'm working on this. This exists. These kinds of things are possible to fix or change or improve. Let's take a look at them and see what we can do about them in the future. So my resume as an AMRexer, if you've seen either of these pictures, hi, that's me. I'm the one who's put those together. If not, spend more time looking at AMReX docs. They're amazing. You got to pay attention to them. I've played around with a large list of things in AMReX over my time. Here's a small list. The last thing I was looking at was MPI improvement, improving our communications. And just looking into what we have to do now on current systems, what we have to do in the future, additional functionality that we might find interesting, cool things that we're kind of leaving on the floor. Load balancing seems to be the next critical step in this. So this is the sporadic slide I put together that is representative of my brain when it comes to why I'm doing this. The first thing is it's fun. That would be this box over here. When you actually look at load balancing, it's actually an incredibly interesting problem to play around with. It is a partitioning problem. It is not a load balancing problem. For example, knapsack isn't knapsack. Knapsack is what you did when you came here. You filled a knapsack with your most critical items of a fixed size. That's the knapsack problem. Load balancing is you throw a pile of change on the floor, you have 15 people, make sure everyone gets a fair share. It's a completely different problem in mathematics. It is often termed the easiest hard problem in that everyone in this room knows what I talk about. Everyone understands this problem. You can spend a career trying to solve it. It is an optimization or scheduling problem that's NP hard. And because it's NP hard and we use approximate solutions to solve it, it looks a lot like a fluid mechanics problem. You don't have a fluid, but you have to verify and validate. It's something you statistically solve. You run a whole bunch of iterations on to try and find the best thing to fit something that works well. And you recursively work on this over time to improve it. So this gives me that sort of sense of working on a fluid mechanics problem without actually having the time to do the full thing. The other two boxes here are, on the right, there have been some recent challenges that have popped up with load balancing. Has anyone had any problem with your load balancer any time in the near past? Has it limited your capability to do something? Has it blown up a simulation, anything like that? I know MFix has. MFix has done all kinds of, wait, MFix isn't in the room. MFix has done all kinds of, there you are. They literally rewrote a whole load balancing strategy because they needed something to help with them with their specific work. So a bunch of things are eking around the edge to me that look like load balancing have a potential to solve, but essentially, there's a lot of incredibly intelligent people here who work around it first. Before we get to the chance to actually do it, we find a workaround to do it some other way. Well, I'd like to look at actually implementing solutions for this right off the bat. Also, the general philosophy of load balancing to the community is good enough, move on, right? The load balancing implementations that we have right now are probably box-lib old, even older. There is so much stuff that has changed since then. So many differences. I've heard them all over the place here today. All these codes trying to couple. All of the physics that were being added in all over the place, the particles of advanced particle applications, so many things have been added. And essentially, we should take a look at this and see if we can do better. So what I've been doing so far. Here's my 4 categories. Number 1, researching and brainstorming. If you see me walking around with a book like this over at Livermore, I'm having a ton of fun. This is my fun, happy place. I'm reading scheduling books and trying to figure out the mathematics. This has made a whole list of possibilities, and I'll give you a short snippet of them at the end of possibilities that we could do to improve your load balancing to solve various problems at the end. But I've been compiling just a giant list of things. I ask your help to keep that list full and coming. I've built a little test space. I've ripped our codes out and put a new little repo and a little test space to iteratively do testing on our AMReX algorithms. Actually, right now, the AMReX is so old and kind of built in that you can only run a load balancing simulation on the size problem that you're running. So if you want to test 256 rank load balancing problem, you need to go get 256 MPI ranks and run it if you do it, the thing buried in AMReX. It's just simply warped and changed in the way that we need it to the time that you can't really test it. So it's been ripped out. And now we could feed in our own rates or generate a artificial set of weights in order to test in it. And that has proved very useful for that box up there. But first, I built a little graph-like object. I do not presume that I can write a graph. but I have a little graph-shaped network object with the idea to collect all the load balancing data in your codes, to instrument them, and collect the data to actually do full-blown analysis on it. It also has a hook into fill boundary. So you can collect your COM data as well and how that is distributed throughout and spit it out. And I haven't built a Jupyter notebook yet because I haven't had a real data test case yet. Someone give me one. But the idea is to spit this out and take a look at all of this data and figure out where shortcomings are. And these have all been combined to have some summer students in 2024 take a look at the SFC and Knapsack studies and make a paper in PERC. I'm going to Columbus, woo. These are the two things they looked at. The right-hand side is the easiest and simplest to think about. There's a combination SFC and Knapsack solver. They did SFC not on the node level, but across, no, not on the rank level, but on the node level. So minimize comms on the most expensive comms off node. And then for the ranks that were assigned to each node, do a knapsack internally to make sure each node has a nice weight balance. So they built one of these. This has been tested a little bit before, but hasn't been tested anytime lately. The second one they did, they came up with off of a Google interview problem called the painter's partition. So when we do SFC, we do a one-pass cut of our 1D line of boxes, and we do something called proportional percentage, which is if you're on 50% of your ranks, don't cut more than 50% of your weight as you go down the line. You just do that common proportional analysis as you go all the way through. Instead, what they did is they just did a binary search for what the best possible cutting location is on your SFC curve. And they got ridiculously good results. So this is just for completion. We'll focus on these two. This is a varying size and the efficiency that the algorithm is going to spit out for all the algorithms. What they did was generated 250 normal distributions, ran each load balancer through it, and then took the mean and the standard deviation of each. So on the top, you have the low standard deviation when all the boxes are similarly sized. Red and purple are SFC. Painters, when it reappears, Painters is now up there with Knapsack. And it's getting efficiency just as good as Knapsack. Down here, you can see when you start varying the box size a little bit, it appears. Here's your green and your yellow. These are the painters, the Google algorithm binary search cut. So essentially, if you've been load balancing with SFC for any time in the near past, you're leaving something like 20%, 15% of the efficiency on the floor based on what you're doing just in the Knapsack, the SFC algorithm alone. So this is essentially giving me that bit of kick that there's low-hanging pieces of fruit that we can tackle in short periods of time, and this isn't been a complete waste of fun, essentially. So what are my plans here? So these are also slides for the summer student. We don't have to read all of this. But the first step is to take this all and put it into a repo that we can all share, a little toolkit. Having algorithms that we're testing, little tests to actually run code and try things out with, data collection utilities, implementations, Jupyter notebooks, anything we put together to make this something that we can explore and investigate. This is my current giant list of ideas. Once again, you don't have to read them all. You can see the summer students crossing them out up there. But there's an absolutely gargantuan list of possible ideas. Feel free to talk to me about anything you see up here. This is part of the generating a discussion component of it. This is a piece of like a 5-page Google Doc on ideas and possibilities and where they might play in. I haven't even gotten to thinking about deep coupled codes or any of the insane stuff I heard here today of all the cool stuff you guys are doing to combine a bunch of random things and how you would load balance it. Coupling is the one that's on my mind because I understand it the best, but there's so many today I haven't even wrapped my brain around. So there's lots of potential possibilities out there. And you're going to see a few in a minute. Now I took that list and I've essentially broken it down into how long it'll take to put it into AMReX and where I could possibly find help to make it happen. So on the top level, you have small frameworks like the summer students did, take SFC and add some stuff to it. Take Knapsack and improve it a little bit. Combine them in interesting ways. The next level is deeper, more complicated things that we know exist elsewhere. For example, networks, graph networks and vector strategies, things like that. And then long-term are things that I'm keeping in the back of my head and just whispering about in certain meetings. When I talk long-term, I'm talking 35 years, for example. If you remember what we were talking about earlier, John. Hint, hint, right? What I'm basically doing here is until the community gives me some specific needs to really target or helps me highlight some specific tasks in this list that would really be helpful for you, I'm building the algorithms and hoping that you'll come. You'll see that they're beneficial, you see that they're useful, you see it exists, and apply it and see what will work. So if you Don't want me to just write algorithms? Give me some ideas. Tell me what your simplifications are, your complications. Tell me what you're doing under the hood to do it. Maybe we can put it into AMReX proper and make some differences. So the rest of this talk is an overview of some of the crazy ideas to hopefully get some juices flowing and get some conversation going. So from the most straightforward on the bottom, it would be fairly simple to add a constraint to both Knapsack and SFC. So for example, make sure there's at least 4 boxes on every rank. Or do the knapsack distribution, but don't put too much memory on a rank that it blows up. That should be incredibly simple to do. The interesting part there is you'd have a failure state. I'm sorry, I can't actually distribute this, and you have to figure out what to do. But otherwise, that is fairly straightforward if you have the correct numbers to put in order to do the work. Another thing, uniform machine or heterogeneous machines. This is you have multiple different types of architecture, using them all effectively. Perlmutter is this system. It has 40 and 80 gigabyte GPUs, and what you might be doing is running a case with a 40 gigabyte GPU, and you just get a couple 80s attached to it. And what's happening is under the hood, it's essentially being treated like a 40, and they're not maximizing it. So instead what you can do is if you have a ratio, just one number to describe how much faster will it go on machine A than machine B, it is fairly easy to take both Knapsack and SFC and put it in the best in either of the 2 buckets, rather than sort it all essentially the same. Essentially, it's just converting cash. Now, here's a pile of change, and there's also some euros in there. Split up the change instead, right? That's a fairly straightforward addition. Getting a little bit more complicated, we currently map GPUs back to the physical ranks with something called least used CPUs. Does anybody have any idea what that is? Exactly. It's a buried little piece of code that nobody really uses. So instead, we could map it taking into account COM information. For example, we could do a small little benchmark at the beginning of every simulation, kind of measuring how far away each node is from every other node. And then having read a bunch of this, I know that most of these algorithms have very simple criteria and extremely effective. So you can do something as simple as take the biggest COM box and put it on the thing that's closest to something else so that the communication is nearest. That would probably be extremely effective. Or make sure that the ones that are farthest apart have nothing on them. These would actually be potentially very, very powerful. And the real trick here would be collecting that information, collecting some information that says how far apart your nodes are to start with. That could be a map that we already know that could be provided, topology. I really like the idea of just having hops. How many hops does a piece of information do from A to B? If I could get MPI to just give me that list, I'd be a happy camper. There's so many uses for that, but oh well. Another one in the back of my mind, there's absolutely no limitation, as far as I can tell, on how long it takes to solve our load balancing simulation, because we already have the capability in AMReX to tuck the load balancer on a side thread. So one strong possibility is if you have a very complicated, detailed linear solver that does a bunch of iterations or takes a really long time, or you just want to run 30 possibilities and pick the best one out, you could collect all your data on step 1, pass it over to a thread the same way we do with async IO. At the end of that thread, just run another time step, and then at the end of that time step, collect the best result out of the load balancer and keep going. So you could just bury complicated, detailed, overloaded load balancing stuff already. The underlying function exists. We could do this right now. We just need to find a case in which you have a complicated load balancer that you want to run and give it a shot. Onto the medium complexity things. These are things that other codes do and have tried out. So unstructured mesh likes to use a graph method. What it does is it defines each cell as a node in the mesh, and each line connects cells that have to share information, say, in your stencil. That's how you describe an unstructured mesh in some cases to begin with. You have an unstructured mesh. How do you know which cell's next to which cell? Then all it does is it goes through and it cuts the mesh so that you have about the same number of nodes while cutting the minimum number of edges. So you load balance and get the minimum amount of columns that you're cutting. For us, we would just weight this graph. Each line would be how much columns are you sending, and each dot would be a box that is of a certain size. So we could take this, convert it into a weighted graph, and potentially do the same thing and account for both in the same time. Then, this is one that WarpX really likes. Charm++ tried to do vector load balancing. This is, instead of having one weight to describe your entire system, have multiple weights. So you have a COM section, then you do a sync. Then you call your mesh. Then you do a sync. Then you do your physics. Then you do a sync. Then you do particles. Then you do a sync. An actual simulation involves a lot of sync steps that actually, if all of them are load imbalanced a little bit wrong, you get more and more and more imbalance built up over time. So the Charm++ has an actual dissertation by Roenick, who made a first attempt at don't just balance one weight, give all the weights over, and we'll balance them all. We'll do the net sum of all of them simultaneously. So this would be a very interesting one. WarpX already thinks this is very interesting because their mesh and their particles scale differently. If all of these scale the same, obviously that's not beneficial, and that might be one of the ways it's been hidden in the background and something we haven't thought about for a while. But if you have multiple pieces of the code that scale at different rates, they call them phases of your code, then this might be a very powerful way to actually get a better load balance that right now is hidden and obscured behind tiny profiler data and information. And here's your long-term thoughts. So the first long-term thought that I keep in the back of my mind is IRI. DOE is now heavily pushing IRI. It has a very wide range of stuff to do. If you don't know what it is, look it up and go to a meeting. It is very valuable stuff. The general idea is advanced workflows and cross-machine initiatives. So here's the simple example I always give. DESI takes a picture of the night sky, sends it off to Perlmutter. Perlmutter quickly looks at the sky and picks out supernovas, galaxies, anything that they really want to get a detailed view of, and send it back to DESI while it continues to scan the night sky. So in the same time window of that person buying that machine and running to run it, it not only scans the night sky, but also gets all the highlighted details and doesn't need to come back later. So it's experiment and computing coupled together. If anybody is doing this type of stuff, there are so many interesting load balancing questions that are literally floating around that nobody has answers to this in general. And so being a part of this conversation, getting AMReX and the AMReX community to be one of the first teams thinking about solutions and pushing and driving it would be really good. Plus, it's the current big initiative. Funding. The second one is quantum. So quantum perfectly fits the load balancing question. The full load balancing question, if you lay it out on the table, is an incredibly high dimensional optimization problem with every single variable you have in your entire code put into one. So this potentially is a very good test case or test idea for all the quantum emulating work that's going on, the quantum algorithm work that's going on. Now this is the 35 years in the future, maybe we'll have one, but 2 people have already published papers on load balancing using quantum code, using actual quantum machines. Now they're officially already outdated analog versions of machines and not digital. But these 2 papers have already been published and have been stared at, and I'm already talking with the NERSC quantum team. This seems like a very good test to try this stuff out in. So I hope this has gotten your brains flowing. I hope this has gotten your ideas about what you can do in your head. Reach out to me and anybody. Find me on the AMReX Slack channel. What can you do in your code to make it faster or better? I have summer students who literally started this week who are going to tackle some of the simpler ones on this list or ones that I presented here directly. And any of those could be next on the chopping block to have an algorithm laying around that you can do to improve your code. So if any of this is interesting, if any of this you want to be a part of, one of my big limitations is I don't have really good unbalanced data to actually work on. You're really using synthetic data. So if you have a case, especially a scalable case, that is load imbalanced and has some cool stuff in it, and you want to know what's going on, just get me the data and walk away. That might be an incredibly powerful thing to do, and I might fix your case. But overall, any sort of conversation, any sort of discussion is welcome. Thank you. I hope you've had a good conference. I hope I saved us a couple of our 10 minutes that we were behind. Thank you very much. Yes.
At some point, AMReX had a version which is compatible with UBE++, right?
Yes.
And do you have any experience with that?
What it has under the hood is also tricky and complicated in terms of load balancing and that kind of stuff. So Charm++ was something in which there was actually a discussion. Andrew, myself, Wei Chen, I think Ann might have been involved in that discussion and whatnot. They put out a funding proposal to take Charm++'s algorithms and generalize them so they're applicable to a wide array of things. We just wanted to essentially sneak into their toolbox and play around. But that funding fell through. And Charm requires you to hook all of your data structures to their data structures to work, which makes it functionally just not useful for us whatsoever. So UPC++ I think had something similar-ish. And it also had a smaller scale of things than even Charm++ did. So I would not actually be opposed to ripping them out, slapping them somewhere, and trying them out. That's fine. That's great. But I don't remember the final state of where those were left. But I would like to. I'll follow up with that. That sounds fun. All right? All good?